Hi everyone, I'm Chris Wolff. I'm a postdoc in Karen Escher's lab. I'm going to change it up a little bit and talk about something a little bit different. I'm sorry I changed my title. We reassessed the data a little bit, so I took sarcopenia out. But so what I'm going to talk about is a bit of a novel concept, or at least we thought people might be interested. And so the main concept is that, right, we're all hopefully a little bit familiar with the hallmarks of aging, right? So a group of cellular processes that are deregulated that contribute to loss of function. And in skeletal muscle in particular, we think of this as decreases in mass, insulin sensitivity, mitochondrial function. But the layer that we add is the circadian clock. So I just wanted to walk through what that is in case you are not familiar. Right, so the circadian clock is a transcription translation feedback loop, and so BMAL and clock are the main transcription. Louder? Oh, laser. This one? Yeah, so BMAL and clock are the main transcription factors that drive the transcription of the period and cryptochrome genes that are then transcribed and translated, and they heterodimerize in the cytoplasm and then return to the nucleus to inhibit BMAL clock. And this process takes about 24 hours to complete. And this happens in every cell and every tissue in the body. And it's autonomous, so it doesn't need input to begin. But the clock also has a set of daily transcriptional output. And so BMAL and clock regulate up to 6,000 genes in some tissues that are expressed daily. And so what we noticed is in most of the young animals, these processes are related to the hallmarks of aging. So we were curious, okay, well, is aging impacting the top part of the clock or the output of the clock? And so what we first did was to see if there's an impact of age at all. And so this is a summary schematic, but basically what we started with was a circadian reporter mouse called the period 2 luciferase mouse. So basically it's a knock-in, and you can excise the tissue, put it in a luminometer, and measure HER2 luminescence for up to, some people do months. So we kept it short and just did a few days. And so, so we get a trace like this. So this is an example. On the x-axis is time in days. On the y-axis is bioluminescence, which is a marker of HER2 protein. So it's basically, this is what the young muscle soleus clock looks like. But then, when we used 24 to 30-month-old mice, what hopefully you can appreciate is that the amplitude of this rhythm is severely blunted in the old group. And so that's quantified in the middle graph, where there's a big reduction in amplitude. We also noticed that the circadian robustness, which is basically the goodness of fit of the cosine wave to this curve, is also severely dampened. So that really led us to the question of how does aging impact the transcriptional program, right? There's an impact on the timing mechanism, but is the program altered as well? So what we did is used 6, 18, and 27-month-old black 6 male mice, and we did a circadian time course collection, so every 4 hours for 2 days. We were all really tired when it was over. And so we took two mice per age per time point, and then we did RNA-seq. And so basically we get a trace like this for every expressed gene, and so we'll have, black will be the young group, blue will be the aged group, and red will be the old animals. And so we used an F-test and a diff circadian package, and then we used the list of circadian genes called with the F-test of P less than 0.01. And so what we noticed first was that the core clock gene BMAL was completely preserved with age. There was no impact on the rhythmicity. But if we looked at some of the repressor genes, so the periods and cryptochromes that feed back onto BMAL, those seem to be impacted by age, which is important because that's how the clock is responding to external stimulus, right? So that's, if you have a dysfunctional repressor limb of the clock, you'll have difficulties with jet lag or phase shifting or responding to things. But then, so when we start to look at the transcriptional program, right, so this heat map, so we have time on the X and then genes on the Y, and you can see that, right, so dark color is like a low expression, and the lighter color is high expression. So if you read across, right, you basically can see the peak and trough of each gene. And so in the young animals, we identified 941 circadian genes, which is in line with what Stefano and basically we were thinking, 1,000 sounds good for muscle. That makes sense. But we were curious, and what we found is that with age, there was a progressive decline in the number of clock output genes. So young, 941, age was 699, and then old was 747. And so that, cool. The clock output went down, but we weren't sure what that meant. So the first step was that, so we then looked at the biological processes that the clock was making up. Right, so in the young animals, it was, these were just a couple of the top pathways, but essentially what we saw was that the clock output in young animals is metabolism, proteostasis, transcription, autophagy. Basically all of the hallmarks were represented in the young muscle clock output. But with age, it started to switch. Right, and so we basically go from all the hallmarks to some of the hallmarks to basically, hey, can we just keep this muscle working, or is it gonna is it dead? And so that it was really kind of striking that there was such a big change. And so now the goal is to go figure out why that happened. So to kind of give a circadian conclusion, right? So we basically see this progressive decline of the clock output with age, which may be in response to the altered repressor genes. It may be, genomic binding sites or inflammation, or we don't know yet, but we're going to start looking. And then basically what we're seeing is that there's this change in clock output and the loss of homeostasis as a circadian control. And I just want to add one more concept. Do I have time? Yeah. So because we had 2 full days of collections, what we could do is collapse our time points on top of each other. So basically we could pool, this 24 hours with this 24 hours and increase our N size, and then look at differential gene expression at different times of day. And so if you think about the animals, we have the active phase in the dark, the rest phase in the light. And so what we did is we looked at 4 different time points, and so basically pooled the samples and looked at differential gene expression with age to see, is there a difference in day, right? So these are non-circadian genes, but it's differential gene expression. And so we were really excited. We were like, I think this is important. And so what we did, I wanted to summarize it quickly, is if you look at different times of day, you get a different number of differentially expressed genes. And then there are some that are always different, right? So for instance, all time points, NF-kappa B signaling in the skeletal muscle is really high all the time. That kind of makes sense. But what we noticed is, in the active phase, autophagy was really upregulated with age. But then in the active to rest transition, it was transcription. There were only 47 genes that were changed during the rest phase, right? So during the light. So if you come in and you take muscle out in the morning and the mice are in the light, you might find less difference. You can add the 136 to the 47, but that's still a small change relative to what you might find at a different time. And then in the rest to active transition, it was metabolic changes. Right? So we were really just kind of struck by the amount of difference based on when you look. Right? It kind of changes. I guess I'll wait till I put the bullet up. Right? But so basically the age-related differential expression varies based on when you look. And so basically pathways that were part of the clock output in the young mice lose rhythmicity and then seem to be dampened all day. And so with that, I'll take questions, and if